Hello there, and welcome to the Sleepy Science Channel. Tonight, we drift into a hidden layer of life that quietly shapes who you are and all the life you see around you. Beneath every thought, every cell, and every moment of change, there is a subtle system at work, a system that listens to experience, a system that responds to time, environment, rhythm, and care. This is the world of epigenetics, a quiet frontier where biology becomes personal, flexible, and full of quiet wonder. A place where DNA is not locked into a fixed script, but is gently guided by your life, and sometimes even your own thoughts. It is where the smallest influences can leave lasting impressions, and where change is always possible. As we explore this landscape together, you may begin to sense how deeply connected your inner world is to the world around you. How experience leaves echoes. How biology is more flexible, more responsive, and more wondrous than it first appears. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your eyes to grow heavy. And let your mind unwind as we explore this fascinating world. Let's begin. Two people can share identical DNA yet develop wildly different traits. Identical twins start from the same genetic blueprint, yet their lives can diverge in ways that feel almost impossible. One develops asthma, while the other breathes easily. One struggles with anxiety, while the other stays calm under pressure. One gains weight easily, while the other does not, even with similar habits. This is not a contradiction of genetics. It is the next layer of the story. Life exposes two bodies to different infections, different stress loads, different sleep patterns, different relationships, and different routines. Over time, those differences accumulate into different instructions being used more often, and different instructions being used less. What makes this so jaw-dropping is that the DNA can stay the same, while the biological settings drift apart. It is like two copies of the same song slowly being remixed into different versions, each shaped by what the world asked of them. Epigenetics means your genes can be turned up or down without changing DNA. Think of your DNA as a complete library you are born with, but your body does not read every book at full volume. Epigenetics is the system that decides what gets read loudly, what gets whispered, and what stays closed on the shelf. That is why the same person can change across life without getting new genes. Your cells constantly adjust which instructions they follow based on signals like sleep, hormones, immune activity, and the demands of daily living. This is not magic, and it is not mood. It is physical control over access and output. It is also one reason health is not destiny. Two people can inherit the same risk and still travel different paths, because the real story is not only what you carry, but what your body chooses to do with it, day after day, moment after moment. Your cells carry the same genes, but epigenetics decides their job. Every cell in your body holds essentially the same genetic instruction set, yet a nerve cell and a skin cell behave like entirely different creatures. That is not because they have different DNA. It is because they are trained to use different parts of it. A neuron must build long connections, handle electrical signals, and keep the brain stable for decades. A stomach lining cell must handle acid, renew quickly, and act like a tough barrier. Epigenetic control is what keeps the neuron from suddenly acting like stomach tissue, and what keeps your skin from trying to think. This is also why injuries heal the way they do. Cells respond based on their identity, and identity is maintained by patterns of gene use that are copied when cells divide. It is the quiet memory that keeps your body organized. A tiny chemical tag can silence a gene for years. Some of the most powerful biological changes come from changes so small you could never see them without specialized tools. A gene can be present, intact, and perfectly readable, yet effectively switched off by a microscopic tag that tells the cell, "Do not run this instruction." What makes that eerie is how long the effect can last. A brief event can set a long-term silence that continues through many rounds of cell division, like a note passed along each time the cell copies itself. This matters because silencing is not neutral. If the muted gene is protective, the cell may become more vulnerable. If the muted gene normally keeps growth under control, the risk profile changes without any DNA letters being damaged. It is a reminder that biology is not only about what exists, but about what is allowed to speak. Sometimes the difference between health and trouble is simply a message of silence. Stress can leave lasting epigenetic marks that change how you react later. Stress is not only a feeling, it is a full-body chemical broadcast. When stress hormones surge, they do not just make your heart race. They enter cells and push gene programs that prepare you for threat. If that alarm system is triggered often enough, the body can start treating normal life like a constant emergency drill. Over time, the genes involved in alertness, inflammation, and recovery can shift in how easily they switch on, like a smoke detector that becomes too sensitive. That can change how strongly you react to future pressure, how quickly you calm down afterward, and how your immune system behaves under strain. This is why chronic stress is so physically expensive. It is not only exhausting in the moment, it can retune your baseline. The haunting part is that the stress may end while the body keeps responding as if it never did. Epigenetics helps explain that lingering echo. Food can reshape gene activity, not just your waistline. Food is information as much as it is fuel. Each meal changes blood sugar, hormones, and the chemical environment that cells use to decide what to build and what to repair. That means diet can influence which biological programs get prioritized. A protein-rich breakfast can push different signals than a sugary one. A long stretch without food can trigger maintenance mode pathways that emphasize cleanup and conservation. Even the same calories can land differently depending on timing, sleep, and stress. What makes this fascinating is that the effects are not only immediate. Repeated patterns can nudge gene activity toward certain long-term habits, like making it easier for the body to store energy or easier to burn it. This is why nutrition advice that ignores biology feels wrong. People are not just counting units. They are sending repeated messages to their cells. Epigenetics is part of how those messages get translated into lasting changes. Smoking can switch off protective genes long after the smoke clears. Cigarette smoke is a chaotic chemical assault, and your body responds by trying to defend itself. But smoke exposure can also disrupt the normal controls that keep cells safe. In lung tissue, and even in blood, researchers can detect long-lasting changes in gene regulation linked to smoke exposure, sometimes years after someone quits. That is mind-blowing because it means your biology can carry a record of past exposure, like a fingerprint. The danger is not only the damage smoke causes in the moment, it is that the safety systems that normally restrain abnormal growth and help repair cellular harm can be reduced in effectiveness when key protective genes are quieted. This helps explain why risk can remain elevated for a long time, even after stopping. Quitting still matters enormously, but epigenetics shows why recovery can be a slow unwinding. The body remembers, even when the habit is gone. Early childhood experiences can echo in gene control for decades. Childhood is not just when you learn words and manners. It is also when your biology learns what kind of world it lives in. In early life, the brain and body calibrate systems like emotion regulation, threat detection, and social safety. Consistent care can help build a nervous system that expects support and recovers quickly. Chaotic environments can push development toward constant vigilance, because that may be what keeps a child functioning in the moment. The striking part is that these early settings can become deeply embedded, influencing how the body interprets normal challenges later on. It is not destiny and it is not a life sentence, but it can shape tendencies. This helps explain why two adults can face the same situation and experience it differently in their bodies, not just their thoughts. Epigenetics gives a mechanism for how early experiences can become long-term patterns in biology, carried forward quietly into adulthood. Some epigenetic changes are reversible, which makes them powerful. The most hopeful thing about epigenetics is that it is not only a story of harm. Because many gene control settings can shift, the body can also move toward repair. This is one reason lifestyle changes can have real biological impact, even when DNA stays the same. The body is constantly rewriting its own operating instructions in response to signals, and some of those rewrites can be nudged in healthier directions. In medicine, this opens a door that feels almost futuristic. Instead of trying to fix a broken gene, scientists can sometimes aim to restore a healthier pattern of gene activity. In certain cancers, for example, some treatments work by reawakening helpful programs that were shut down. That idea is astonishing. It suggests that some diseases are not only problems of broken parts, but problems of misset controls. When controls can be adjusted, new kinds of healing become possible. Reversibility turns epigenetics from a warning into an opportunity. Epigenetics helps explain why nature versus nurture is the wrong question. People love choosing sides. Either your genes made you, or your environment made you. But biology does not work like a debate. It works like a conversation. Genes provide possibilities, and experience helps decide which possibilities get used more often. That means nature and nurture are not enemies. They are partners, constantly shaping outcomes together. This also explains why simple answers fail. A person can inherit a vulnerability and never develop the problem, while another person with a lower genetic risk might, depending on what their body has been signaling and absorbing over time. It helps explain why families can share patterns without sharing identical fates, and why the same intervention can work brilliantly for one person and barely touch another. The deeper point is this: your biology is responsive. It is not a fixed script that runs unchanged from birth. Epigenetics is one of the clearest reasons humans are adaptable, for better and for worse. A fertilized egg resets many epigenetic marks to start fresh. Right after conception, the new embryo has a problem to solve. It must become every cell type in the body, even though sperm and egg arrived with very different histories. So the early embryo performs a dramatic cleanup, wiping and rewriting many gene control settings, so development can begin from a blanker slate. This reset is not total. A small number of marks resist the erase, and that exception matters. It helps explain why certain parent-specific effects can survive into the next generation. It also explains why early development is so delicate. If the reset goes wrong, cells can receive confusing instructions at the exact moment they are choosing their futures. The stunning takeaway is that your life begins with a biological reboot, a quiet reconfiguration that prepares one cell to build a whole person, step by step, without changing the DNA text. Cells use epigenetic locks to remember who they are. If your cells forgot their identity, your body would become chaos. A skin cell might start acting like a liver cell. A muscle cell might start following brain-like programs. The reason that does not happen is that cells keep a living memory of their role. When a cell divides, it does more than copy DNA. It also copies instructions about what to keep active and what to keep quiet, so the new cells stay on the same career path. That memory is surprisingly stubborn. It is why your eyebrows reliably regrow as eyebrows, not as random tissue. It is also why healing has limits. Many cells cannot easily switch to a completely different identity, even when that would be useful. Scientists learned this the hard way when they tried to convert one adult cell type into another. The locks are real. They keep your body stable, predictable, and beautifully organized. Your liver cell stays liver by maintaining specific gene off switches. A liver cell does not become a liver cell once and relax. It actively maintains its identity every day. It must keep detox systems ready, manage nutrients, and produce proteins that circulate through your bloodstream. To do that, it keeps a huge number of non-liver programs shut down, not because they are harmful, but because they would be distracting. Imagine trying to run a busy kitchen while someone constantly hands you sheet music, construction plans, and legal contracts. That is what the genome is like. The liver cell must ignore most of it to excel at its job. When liver cells are damaged, this identity system becomes even more important. Repair has to happen without losing the liver's specialty. If the off switches weaken, cells can drift into confused states that do not behave properly. This is one reason liver disease can be so complex. It is not only injury, it is also identity under pressure. Histone proteins act like spools that tighten or loosen DNA access. Your DNA is far too long to sit neatly inside a cell without clever packing. So it wraps around histone proteins, like thread around spools. But this is not just storage. The tightness of that wrap controls whether a gene region is easy to reach or hard to reach. When DNA is packed tightly, the cell's reading machinery struggles to access the instructions. When it loosens, genes become available, like opening a door in a hallway that was previously bricked up. What makes this thrilling is how dynamic it can be. Cells tighten and loosen different regions depending on what they need right now, such as fighting an infection, building new proteins, or responding to hormones. It means the genome is not simply a list of instructions. It is a physical landscape that can be rearranged. Access itself becomes a form of control, and that control can change with context. DNA methylation is like a quiet, do not read sign. This one small chemical mark is used as a powerful control system in the genome, and it shows up in places you might not expect. One dramatic role is defense. Your DNA contains ancient hitchhiker sequences that can cause trouble if they wake up and copy themselves. Methylation helps keep many of those sequences suppressed, protecting the stability of cells over a lifetime. Another role is long-term patterning. Some genomic regions stay methylated in consistent ways across tissues, acting like guardrails that keep gene activity from drifting into risky territory. This is why methylation patterns can become useful clues. Scientists can sometimes read them like a molecular diary, revealing age-related changes or exposure histories in a way that feels almost like forensics. The awe-inspiring part is that a tiny mark, repeated across the genome, can quietly shape what is allowed to happen inside your cells, minute after minute, year after year. Some genes are designed to be active only from one parent. This is one of biology's strangest rules. For a select set of genes, your body intentionally uses only the version from your mother or only the version from your father. The other copy is present, intact, and still gets carried in every cell. Yet, it is meant to stay quiet. Why would evolution build redundancy and then refuse to use it? The answer seems tied to a tug-of-war over resources during development. Certain growth-related genes can influence how strongly a developing baby draws nutrients, and parent of origin patterns may have evolved as a kind of negotiated balance. The result is eerie and precise. Your body is not simply using the best copy. It is following a rule about whose copy gets the microphone. When that rule is disrupted, it can have outsized effects on growth and brain development. It is a reminder that inheritance is not only DNA sequence. It is also instructions about which parent's voice counts. Genomic imprinting can make a parent's copy permanently muted. Imprinting is the mechanism that enforces the one-parent rule, and it is astonishingly strict. Before you are even born, certain genes are tagged with a parent of origin identity, and that identity can persist as your cells multiply into trillions. That means the consequences of an imprinting error are not easily corrected later. If the active copy is missing or damaged, the quiet copy usually cannot simply step in and help, because the system is designed to keep it silent. This is why imprinting disorders can be so puzzling. The DNA may contain a perfectly healthy backup, yet the body treats it like it does not exist. What makes imprinting feel almost poetic is how it connects generations. It is a biological signature carried from parent to child, shaping development through rules that are older than any individual. It is also one of the clearest examples that gene activity is governed by context and history, not only by the letters of DNA. X chromosome inactivation silences one X in many female cells. Females typically have two X chromosomes, but cells avoid a double dose of X-linked genes by shutting down most of one X in each cell. This is not a gentle reduction. It is a major cell-wide decision that creates a quiet X and an active X, and that choice is made early in development. The astonishing part is that the choice is usually random from cell to cell. In some cells, the maternal X stays active. In others, the paternal X stays active. Once a cell commits, its descendants tend to keep that same choice. This matters for real-life health. If a harmful X-linked variant is present on one X, the body can become a mosaic of cells that do and do not express it, which can change the severity of certain conditions. It also means that two people with the same X-linked variant can experience it differently. A fundamental biological balancing act creates individuality at the cellular level. That silencing creates a patchwork of active X genes across tissues. Because different cells keep different X chromosomes active, the body becomes a living patchwork. You can think of it like a quilt stitched from two fabrics, woven together in tiny pieces across organs. This is not just a cute metaphor. It can influence how traits show up in the real world. Some X-linked features can appear in a mottled pattern, especially in tissues where neighboring cells stay clustered as they grow. In medicine, this patchwork can complicate diagnosis. A blood test might show one pattern while another tissue behaves differently, because the mix of active X choices can vary by body region. It can also buffer certain risks. If a problem-causing variant is on one X, having a blend of cells can reduce the overall impact compared to having every cell express it. The wild idea here is that you are not one uniform expression of your X chromosome. You are a carefully balanced mixture, and that mixture can matter. Calico cats show epigenetics in fur color patterns. A calico cat is a walking lesson in gene control, visible from across the room. The orange versus black coat color trait is linked to the X chromosome. Female cats often carry two different versions, one on each X. Early in development, different skin cell lineages keep different X chromosomes active, and those lineages expand as the kitten grows. The result is bold islands of orange and black, Not because the DNA changes from patch to patch, but because different groups of cells choose different active X chromosomes and stick with that choice. The pattern is not painted on top. It has grown from within. That is why every calico has a unique map, like a fingerprint. It also explains a famous detail. Most calicos are female because the 2X setup makes the patchwork possible. A coat becomes a biography of early cellular decisions turned into color. It is epigenetics made obvious, and it is unforgettable once you know what you are seeing. Identical twins often grow more epigenetically different with age. Early in life, their gene activity settings can look remarkably similar, like two phones shipped with the same configuration. Then, life starts tapping the screen. One twin works night shifts, the other sleeps early. One gets a stubborn virus, the other does not. One moves to a polluted city, the other lives near the sea. None of that changes the DNA letters, but it can slowly reshape which genes are easier to use and which stay quiet. Scientists can actually measure this drift by reading patterns of gene control across the genome. What makes it uncanny is how these differences can stack up silently for years before anything obvious appears. Later in life, those hidden settings can help explain why one twin develops a disease first, or responds differently to the same medication, despite the same starting blueprint. Aging is not just time passing. It is regulation changing. The same gene can be loud in one tissue and whisper elsewhere. This is not a contradiction. It is the whole point of a body. A gene for digesting milk sugar matters in the small intestine, where food arrives, but it is almost irrelevant in your fingertip. A gene that helps your retina sense light needs to be highly active in the eye, yet nearly silent in the liver. Epigenetic control makes this precision possible by changing access. In one tissue, the DNA around a gene is opened, inviting the cell to read it repeatedly. In another tissue, that same region is tucked away, like a tool stored on a high shelf because it is not needed. This is why blood tests do not tell the full story of what is happening in the brain, and why a drug can affect one organ strongly while barely touching another. One genome serves many roles by allowing different volumes in different places. Epigenetics is how one genome builds a brain and a bloodstream. During development, the same DNA must generate cells that think, cells that carry oxygen, cells that contract, and cells that form barriers. That requires timing so precise it feels choreographed. Early cells are flexible, then choices begin. Some commit to becoming neurons and start building machinery for signaling and long-term survival. Others commit to becoming blood stem cells and prepare for constant renewal and rapid response. These decisions are reinforced again and again as layers of gene activity are turned on, while other programs are firmly shut down. There is no master controller issuing commands. The instructions are local, responsive, and self-reinforcing. This is why development usually succeeds, and why small disruptions at critical moments can have large consequences later. One genome becomes many specialized systems through disciplined control, not through rewriting instructions. Cancer often involves broken epigenetic breaks, not only broken genes. Many people imagine cancer as a collection of damaged DNA, like a book filled with typos. Sometimes that is true. But cancer can also arise when the text is mostly intact and the controls fail. Healthy cells follow strict rules about when to divide, when to stop, and how to cooperate with their neighbors. Those rules are enforced by gene activity patterns. When those patterns unravel, cells can slip into immature, aggressive states that favor growth over order. This is why cancer cells often look less specialized under a microscope. They have not only gained power, they have lost identity. The unsettling part is that this can happen without breaking genes at all. Misset controls alone can be enough. Cancer is often a problem of regulation gone missing, not just parts gone wrong. Tumors can silence DNA repair genes without mutating them. Imagine owning a perfectly functional smoke alarm that no longer makes noise because the speaker is taped over. That is what happens when a tumor shuts down a DNA repair gene through gene control rather than damage. The gene still exists, but the cell no longer uses it. Without repair systems actively scanning for mistakes, copying errors accumulate more easily, making the cell increasingly unstable. This instability gives tumors an advantage by speeding up change and adaptation. In certain colon cancers, a key repair gene is frequently silenced this way. Similar effects appear in some breast and ovarian tumors involving important protective genes. This is why modern cancer testing looks beyond mutations. Sometimes the danger is not a broken instruction. It is a safety system that has been deliberately muted. Some cancer drugs work by restoring normal epigenetic settings. Instead of attacking tumors with blunt force, some treatments aim to reawaken silenced control systems. These medicines do not rewrite DNA. They change how tightly instructions are locked away. In certain blood cancers, drugs that reduce excessive gene silencing can allow protective programs to speak again. When that happens, cancer cells may slow their growth, regain sensitivity to normal stop signals, or become more likely to self-destruct. Other treatments loosen overly tight DNA packaging, so helpful genes become reachable once more. This strategy feels almost counterintuitive. Rather than killing cells outright, it encourages them to behave properly again. The promise here is enormous. If disease can arise from misset controls, then healing can sometimes come from restoring balance rather than escalating destruction. Epigenetic changes can help cancers hide from immune detection. Your immune system constantly scans cells for signs of danger. Tumors survive by learning how to blend in. Through gene control changes, some cancers reduce the signals that would normally alert immune cells. Others interfere with the machinery that displays suspicious proteins on the cell surface. These tactics do not require genetic damage. They require silence. The result is a tumor that exists in plain sight but does not raise the alarm. This helps explain why immune-based treatments succeed dramatically for some patients and fail for others. If the tumor has epigenetically hidden its warning flags, the immune system has little to grab onto. Researchers are now exploring ways to reverse this invisibility, making tumors more visible before unleashing immune attacks. Sometimes the key is not stronger weapons, but better lighting. Viral infections can rewire epigenetic controls to favor viral survival. Viruses are masters of manipulation. With very little genetic material, they hijack a cell's control systems to create a safe home. Some viruses suppress antiviral genes that would normally summon immune defenses. Others push cells into quiet, dormant states that allow the virus to persist unnoticed for years. Herpes viruses are particularly skilled at this, slipping in and out of silence. Human immunodeficiency virus also relies on deep control tricks that make complete elimination difficult. What makes this remarkable is that viruses can influence how DNA is packaged and accessed, reshaping which cellular instructions are even available. This is not brute force. It is strategic rewiring. When an infection becomes lifelong, it is often because the virus has altered the rules of gene control inside the cell itself. Certain viruses push cells into states that promote uncontrolled growth. Some viruses interfere with the cellular safeguards that keep growth under control. Human papillomavirus is a clear example. Its proteins disrupt key safety checkpoints, allowing infected cells to divide when they should stop. Over time, this increases cancer risk. Epstein-Barr virus can push certain immune cells to survive and multiply longer than they normally would, occasionally contributing to lymphomas. Hepatitis B and hepatitis C create a different path by driving chronic liver inflammation, forcing cycles of damage and repair that raise long-term risk. What makes this deeply compelling is the public health connection. Preventing infection through vaccination or screening is not only about avoiding illness now. It is about preventing the slow creation of dangerous cellular states years down the line. A virus can quietly reshape a cell's future. Your immune cells use epigenetics to remember past threats faster. Beyond antibodies, the immune system learns in a broader way. After certain infections or vaccines, some immune cells become primed to respond more quickly and forcefully to future danger. This is not memory of one specific invader. It is a general readiness upgrade. Epigenetic changes help explain how this happens. Genes involved in rapid defense can be kept in a more open, accessible state, allowing faster activation when trouble appears. This phenomenon helps explain why some early exposures influence immune behavior later in life, and why certain vaccines seem to offer benefits beyond their main target. Your immune system is not just reactive, it is adaptive. It learns patterns, adjusts thresholds, and fine-tunes its response based on experience. Gene control is part of how that learning is stored. Learning can trigger epigenetic changes in neurons tied to memory. When you learn something new, your brain does not just store a ghostly idea. It has to physically strengthen certain connections between neurons, and that requires building specific proteins at the right synapses at the right time. Epigenetic control helps make that possible. Learning signals can open access to particular gene regions, so neurons can produce the materials needed to reinforce a memory trace. What makes this feel mind-bending is that your experiences can reach down into the nucleus of a brain cell and change which instructions are easiest to use next time. In animal studies, blocking certain epigenetic processes can weaken memory formation, as if the brain cannot fully save what it just lived through. This turns learning into a biological journey. A conversation, a skill, a fear. A song can leave a molecular footprint that nudges future responses. Memory is not only stored in electrical activity, it is supported by gene control adapting to experience. Some memory genes are controlled by methyl tags that come and go. Not all gene control marks are permanent. Some behave more like sticky notes that can be placed, removed, then placed again, depending on what the brain needs. In memory circuits, that flexibility is crucial. Neurons must sometimes keep certain genes quiet to stay stable, but then quickly allow those genes to activate during learning and quiet them again afterward. Methyl tags are one way this can happen. The astonishing part is the timing. These changes can occur on a human scale, over minutes to hours, not only over years. That means a memory is not simply written once. The brain uses shifting access to instructions to shape what gets strengthened, what gets trimmed, and what gets consolidated. This is part of why practice works. Repetition keeps reopening the same biological doorways, making the pathway easier to activate next time. It is also part of why forgetting is normal and useful. The brain can remove access where it is no longer needed. Memory is a living process, not a static filing cabinet. Sleep loss can shift gene activity patterns linked to brain function. A sleepless night is not only tiredness. It is a change in how the brain runs its internal maintenance. During healthy sleep, the brain cycles through states that support repair, synaptic tuning, and the balancing of chemical signals. When sleep is cut short, the brain has to operate without completing that overnight reset. Epigenetic shifts can accompany this, changing which gene programs are prioritized. Some patterns are linked to inflammation, stress signaling, and reduced support for learning and attention. That helps explain why sleep loss can make the world feel louder, emotions feel sharper, and decisions feel harder. It is not weakness. It is biology reallocating resources. The chilling part is that repeated sleep disruption can push these patterns toward becoming a new normal, making it easier to slip into the same fog again. The hopeful part is that sleep is also a powerful signal in the other direction. Rest can help restabilize gene activity patterns, restoring the brain's ability to regulate itself cleanly. Circadian rhythms coordinate daily epigenetic changes across many organs. Your body is not doing the same thing all day. It runs on a schedule, and that schedule reaches deep into gene control. Circadian rhythms act like a conductor, cueing waves of activity in the liver, gut, muscles, immune system, and brain. At certain times, genes involved in energy use and digestion are more active. At other times, repair and cleanup programs take priority. Epigenetic control helps make these shifts smooth by opening and closing access to different gene sets on a daily cycle. This is why the same meal can land differently depending on when you eat it, and why certain symptoms worsen at predictable hours for some conditions. It is also why jet lag feels so brutal. Your environment says it is morning, but your organs are still running last night's program. The fascinating truth is that you are not one steady body. You are a body that changes its internal settings with the clock, coordinating millions of cellular decisions so you wake, move, digest, recover, and sleep in rhythm. Light exposure can influence epigenetic timing signals in the brain. Light is not just something you see. It is a biological command. Specialized cells in the eye send signals to a master clock region in the brain, helping set your internal time. That clock then influences hormone release, body temperature, alertness, and sleep pressure. Epigenetic mechanisms help translate these timing signals into gene activity patterns that match day and night. This is why bright light late in the evening can make sleep harder, even if you feel exhausted. The body interprets light as a message that the day is still happening, and it adjusts internal programs accordingly. Morning light does the opposite. It anchors the clock, helping stabilize sleep and wake timing. What makes this captivating is how simple the lever is. Photons hitting your retina can reshape daily gene control in the brain and ripple outward into the body. It also explains why seasonal changes affect mood and energy for many people. Light is a quiet editor of your biology, guiding when certain programs should run and when they should wait. Exercise can activate genes for energy use through epigenetic pathways. When you exercise, your muscles do not merely burn fuel. They send urgent signals that change what the body prioritizes. Muscle contraction shifts calcium, energy molecules, and stress responses inside cells, and that can lead to epigenetic changes that make certain genes easier to activate. These genes support energy production, glucose handling, and the building of new mitochondria, the cell's energy factories. That is why regular movement can change your baseline metabolism. It is not only burning calories during the workout, it is adjusting the machinery that decides how fuel is used afterward. What makes this feel like a superpower is that the signal is physical. Your body responds to what it is asked to do, and it rewrites patterns of gene activity to meet that demand more efficiently next time. This helps explain why exercise can improve insulin sensitivity and endurance even before visible body changes appear. You are training gene programs, not just muscles. The workout is a message, and the body listens. Muscle remembers training partly through lasting epigenetic adjustments. Anyone who has trained, stopped, and then returned knows the eerie feeling of getting strength back faster than the first time. Part of that may come from lasting changes in muscle tissue that make certain growth and repair programs easier to restart. Epigenetic adjustments can keep key regions of DNA more accessible, like leaving tools laid out on a workbench instead of packed away in a closet. When you resume training, the body does not have to reinvent the entire response from scratch. It can reactivate familiar pathways more quickly. This is one reason a short period of consistent training can have benefits that linger beyond the last workout, even if performance later fades. It also adds a hopeful perspective for people starting again after illness or a long break. Progress is not always erased. Some of the groundwork can remain, quietly stored in how muscle cells manage gene access. The idea is simple and thrilling. Your body keeps a record of effort, and that record can make future effort more effective. Inflammation can switch on gene programs that stay active too long. Inflammation is meant to be a short-term rescue response. It calls immune cells to a problem, raises defenses, and supports healing. But when inflammation becomes chronic, the body can get stuck in a defensive posture that damages healthy tissue. Epigenetic changes can help explain why this stuck state is so hard to break. Repeated inflammatory signals can make certain immune genes easier to turn on, so the system becomes quick to flare, even when the original trigger is gone. It is like a neighborhood where every small noise sets off alarms because the wiring has been sensitized. This matters across many conditions, from joint pain to heart disease risk. The body is not only reacting, it is learning a pattern. The good news is that patterns can change, but they often require sustained signals in the opposite direction. This is why sleep, stress reduction, and nutrition can matter for inflammation in ways that surprise people. They are not just comfort tips. They can influence whether defensive gene programs stay activated or finally quiet down. Chronic stress hormones can alter gene control in key brain regions. Stress hormones are designed to help you survive short bursts of danger. They sharpen attention, mobilize energy, and make the body ready to act. The problem is chronic exposure. When stress hormones stay high for long stretches, they can influence gene control in brain regions involved in threat detection, mood, and decision-making. That can change how strongly you perceive danger, how quickly you recover after a scare, and how easily you feel overwhelmed. The frightening part is that this can become self-reinforcing. A brain tuned toward vigilance notices more threats, which triggers more stress, which deepens the tuning. Epigenetic mechanisms can contribute by shifting how readily certain stress response genes switch on in those circuits. This offers a different kind of compassion. Some people are not simply overreacting. Their biology has been trained by experience to stay on guard. It also offers a route forward. If the brain can be tuned by sustained stress, it can also be tuned by sustained safety, support, sleep, and healthier rhythms. Regulation is not fixed. It can move. Social experiences can change epigenetic marks in animal brain studies. In animal studies, social environment can reach into the brain and change gene control in ways that affect behavior. Supportive bonding, social stability, and predictable caregiving can shape stress regulation pathways. Isolation, social defeat, or unstable social conditions can shift those pathways differently, sometimes making animals more anxious or less resilient. What makes this so gripping is that it turns social life into a biological force, not a soft extra. The brain is built to interpret relationships as signals about safety. When the social world feels dangerous, the body prepares for danger. Epigenetic changes are one mechanism researchers study to explain how these experiences can leave lasting effects even after the situation changes. This does not mean humans are trapped by early social pain. It means social experience has weight. It also helps explain why connection can be healing in more than an emotional sense. Safety, belonging, and support can shift physiology, not only feelings. The social world can write on the brain's control systems, and that is both sobering and hopeful. Nurturing care in early life can shape stress genes long term. A baby is not only growing, it is calibrating. Early care teaches the body what to expect from the world. Consistent soothing, warmth, and predictable support can help build a stress system that switches on when needed, then switches off cleanly. In animal research, differences in maternal care have been linked to lasting changes in how stress-related genes are regulated in the brain, affecting how strongly the stress response fires later. The breathtaking part is the logic. If early life feels safe, the body can afford to invest in exploration and recovery. If early life feels unpredictable, the body may prepare for threat by staying more alert. Those patterns can influence sleep, emotion regulation, and even immune balance as the years pass. This is not about blame. It is about mechanism. Early nurturing can act like a biological training signal that teaches the nervous system, at the molecular level, how to return to calm. The body learns safety, and then it remembers how to find it. Trauma can be linked to measurable epigenetic differences in stress pathways. Trauma is not only a memory in the mind, it can become a pattern in the body. Studies have found associations between traumatic exposure and differences in gene regulation connected to stress hormones and inflammation, including changes in methylation at key stress-related genes. What makes this so striking is that the body can carry traces of extreme experience in a form that can be measured, not guessed. People often describe feeling on edge even when life is finally stable, or feeling numb when they want to feel present. Epigenetic shifts offer one explanation for why the alarm system may stay tuned too high or too low. It is like the body learned that danger can appear without warning, so it keeps its defenses close. This does not mean healing is impossible. It means healing may require more than willpower. Safety, therapy, community, and time can help retrain the system. Epigenetics turns trauma into something we can study with compassion and precision, and that makes the path forward clearer. Nutrition during pregnancy can influence fetal gene settings. During pregnancy, food is not only supporting a mother, it is shaping the chemical environment in which a developing baby's cells decide how to operate. Nutrients help build tissues, but they also supply ingredients the body uses for gene control, including the molecules needed for methyl tagging. That makes pregnancy a time when nutrition can subtly influence how certain genes are regulated as organs form and mature. The fascinating part is that the fetus is not passively receiving calories. It is gathering signals about the outside world through the mother's biology, including stress hormones, inflammation, and nutrient patterns. Those signals can shape priorities, such as how energy storage systems are tuned or how growth is balanced across tissues. This is one reason prenatal care emphasizes basics like balanced nutrition and avoiding severe deficiencies. It is not just about birth weight. It is about long-term settings. Epigenetics suggests that early development is a period of extraordinary sensitivity, when small differences can echo into lifelong biology. Famine exposure has been associated with later metabolic health changes. When a population experiences famine, the most obvious harms are immediate. But some of the most haunting effects appear years later. Historical studies have linked prenatal famine exposure with higher risks of metabolic problems in adulthood, including differences in glucose regulation and heart health. The proposed story is chillingly practical. If a developing fetus receives signals of scarcity, the body may be tuned towards saving energy and storing fuel whenever possible. That tuning can be helpful in a world that stays scarce. But if the world later becomes food-rich, the same settings can become a disadvantage. Epigenetic differences have been reported in people exposed to famine during early development, including changes near genes involved in growth and metabolism. This does not mean famine writes fate. It means early survival strategies can carry forward. The deep wonder here is that a temporary crisis can leave a biological footprint that outlasts it by decades. It is one of the clearest examples of history entering the body, not as a story, but as regulation. The placenta uses epigenetics to manage nutrient flow to the fetus. The placenta is not a passive pipe. It is an intelligent interface that negotiates what gets delivered to a developing baby, when and in what amounts. It senses signals from the mother's body and adjusts transport, hormone production, and immune interactions. Epigenetics helps coordinate this high-stakes work by regulating which placental genes are active at different stages of pregnancy. That matters because pregnancy is a moving target. Early on, the placenta must help establish and protect the pregnancy. Later, it must manage growth demands, oxygen delivery, and nutrient exchange at a massive scale. If the placenta misreads signals or its gene control is disrupted, growth patterns can change and risks can rise for both mother and baby. What makes this captivating is that the placenta is temporary, yet it performs one of the most complex jobs in biology, then disappears. It is a short-lived organ that can shape lifelong outcomes using gene regulation to adapt moment by moment. Epigenetics gives us a window into how that adaptation is orchestrated. Some developmental disorders come from imprinting errors, not missing DNA. Some disorders are not caused by losing genes or breaking them. They are caused by using the wrong parent's copy, or by failing to follow the parent's specific rules that normally control certain genes. That is what makes imprinting disorders so bewildering. A person can have the correct DNA sequence, yet the body reads it incorrectly because gene activity is misassigned. This can affect growth, appetite, learning, and behavior because many imprinted genes are heavily involved in development. The core mystery is that imprinting is like a label attached before birth that says, use this copy and ignore that copy. If the label is missing, swapped, or misapplied, the outcome can be dramatic. In some cases, a gene that should be active is silent. In other cases, a gene that should be silent becomes active. The same DNA can lead to different results depending on which parent it came from. That idea feels almost impossible until you realize it is a rule-based system built into normal biology. Epigenetics makes those rules visible, and that visibility helps medicine. Angelman syndrome involves parent-specific gene activity in the brain. In certain parts of the brain, a key gene is meant to be active mainly from the maternal copy, while the paternal copy is usually kept quiet. Angelman syndrome can arise when the maternal copy is missing or not functioning properly in those neurons, because the quiet paternal copy typically cannot compensate. The result is a distinctive developmental condition that can include severe speech impairment, movement and balance challenges, seizures, and a characteristically happy demeanor with frequent smiling and laughter. What makes this astonishing is the logic. The brain contains a usable gene copy, yet the rules of gene activity prevent it from stepping in. This is epigenetics, turning a backup into silence. It also points to a fascinating therapeutic idea. If the paternal copy could be safely reactivated in the right brain cells, it might partially restore function. Researchers have explored ways to do exactly that, aiming to lift the normal silencing and let the quiet copy speak. Angelman syndrome is heartbreaking, but it also shows how understanding gene regulation can transform a condition from mysterious to mechanistically clear. and potentially more treatable. Prader-Willi syndrome involves a different parent-specific gene pattern. Prader-Willi syndrome flips the imprinting story in a different direction. In this case, a cluster of genes in a specific chromosome region is normally active from the paternal side, while the maternal versions are typically silenced. When the paternal contribution is missing or inactive, those genes are not properly expressed, leading to a striking pattern of symptoms. Infants may have weak muscle tone and feeding difficulties at first, then later develop intense hunger, slow metabolism, and a high risk of obesity without careful management. There can also be learning challenges and behavioral difficulties, often tied to impulse control and routine. The deeply fascinating part is how specific the failure is. The DNA is not necessarily broken across the board. The problem is that the body is missing the parent-specific expression it expects, like a duet where one voice never enters. This makes Prader-Willi a powerful demonstration that development depends not only on having genes, but on having the correct parental pattern of activity. It also explains why diagnosis often focuses on imprinting tests, not only sequencing. Epigenetic mistakes can disrupt growth, even with normal gene sequences. Development is like building a skyscraper while also writing the instruction manual as you go. Timing is everything. If Jean control signals fire too early, too late, or in the wrong tissues, growth can shift off course, even when the DNA letters are perfectly normal. Epigenetic mistakes can alter how strongly certain growth programs run, how organs mature, and how the body balances resources. This is why some children have unexplained growth differences that are not traced to a clear mutation. The wiring of regulation may be the issue. It is also why two people with the same genetic variant can have different severity. The variant is not acting alone. It is acting inside a regulatory environment that can amplify it or soften it. What makes this both unsettling and hopeful is that regulation is, in many cases, more adjustable than sequence. Understanding epigenetic errors can shift medicine away from nothing is wrong with your DNA toward we can see what is misset. That can open paths for monitoring, support, and targeted therapies that focus on function, not just code. Assisted reproduction can coincide with subtle epigenetic differences in some cases. Assisted reproduction often involves early embryos developing in conditions that differ from the body's usual environment, such as laboratory culture and carefully timed procedures. Most children conceived this way are healthy, yet researchers have explored whether a small subset of cases shows subtle differences in gene regulation, especially in imprinted regions that are known to be sensitive during early development. This is not a scare story. It is a scientific question about timing. Imprinting marks and other gene control settings are being established and maintained at the very stage when embryos are handled and cultured. Even tiny shifts in conditions could, in theory, influence these settings in rare situations. Some studies have reported slightly higher rates of certain imprinting-related disorders after assisted reproduction, though the absolute risks remain low and the research is complex. The fascinating takeaway is how sensitive early development can be. It is like setting the initial defaults on a new system. Understanding these mechanisms helps clinics keep improving protocols, optimize culture conditions, and reduce risks further. Epigenetics here is not about fear. It is about precision, refinement, and making a powerful technology even safer. Aging is linked to predictable epigenetic shifts across the genome. If you could watch your cells age in slow motion, you would not only see wear and tear, you would see patterns of gene control changing in surprisingly consistent ways. Across many tissues, certain regions of the genome tend to gain or lose regulatory marks as time passes, and those shifts line up with changes in repair capacity, inflammation, and cellular identity. The most fascinating part is that this is not random chaos. researchers can recognize age-related signatures that appear across large groups of people, suggesting the body follows a kind of aging script at the level of regulation. This helps explain why aging is more than wrinkles. It is a coordinated shift in which maintenance programs run strongly and which ones fade. It also helps explain why two people with the same birth date can feel different inside. The timing of these shifts can speed up or slow down depending on life history. Aging is not just a clock. It is Joule regulation, gradually changing its priorities. Epigenetic clocks can estimate biological age from methylation patterns. Imagine taking a tiny sample of blood and getting a readout that guesses how old your body seems, not how old your calendar says you are. That is the promise of epigenetic clocks. They use patterns of methylation at specific sites in DNA that tend to change with age in recognizable ways. What makes this so jaw-dropping is accuracy. Some clocks can predict age within a few years for many people, suggesting the body leaves a measurable signature of time in how it regulates genes. Even more intriguing, when someone's epigenetic age appears older than their actual age, it can correlate with higher risk of certain diseases and earlier mortality in some studies. That turns methylation into a kind of biological weather report. It is not fate. It is a signal. The deeper wonder is that you can track aging as a molecular process, not just as candles on a cake. It is one of the clearest examples that epigenetics can translate invisible biology into something you can measure, compare, and potentially influence. Lifestyle factors can speed up or slow down epigenetic aging signals. Two people can share the same birthday, yet one seems to age faster at the molecular level. Lifestyle is one reason. Sleep quality, chronic stress, smoking, diet patterns, and physical activity can all influence the chemical environment that shapes gene regulation over years. Some studies show that healthier behaviors are associated with younger-looking epigenetic clock readings, while harmful exposures are associated with older-looking readings. The thrill here is not a simple promise of control. It is that the body appears to keep score. Your daily choices and conditions can nudge the pace at which regulatory patterns drift. This gives a concrete mechanism for why lifestyle changes sometimes feel powerful, even when nothing about your DNA has changed. The message to a viewer is not moral judgment. It is possibility. If aging includes adjustable regulatory settings, then the story is not only decline. It is feedback. It is the body responding to signals and recalibrating over time. Your habits are not just actions. They are long-term instructions. Certain medications can shift epigenetic markers tied to aging pathways. Some medicines do more than target symptoms. They can alter the cellular programs that shape aging-related biology. For example, treatments that reduce chronic inflammation can indirectly influence gene regulation, because inflammation is a powerful driver of long-term changes in cellular behavior. Other drugs affect metabolism, hormone signaling, or stress systems, and those systems feed directly into the chemistry that supports epigenetic tagging. In research settings, scientists also study compounds that directly influence enzymes involved in adding or removing regulatory marks, exploring whether they can restore more youthful patterns of gene activity in specific contexts. This is not a guarantee of longer life. It is a demonstration of leverage. If a medication shifts the internal environment, the genome's settings can respond. That makes aging feel less like a single unstoppable process and more like a set of interacting dials. It also raises fascinating questions about side effects. If a drug changes gene regulation in one beneficial pathway, what else might it quietly shift? Epigenetics helps explain why medicines can have long echoes beyond their immediate target. Epigenetic drift means gene control becomes noisier over time. As we age, genre regulation can become less precise, like an orchestra slowly losing its conductor. Cells that once followed crisp patterns of on and off may start showing more variability, even within the same tissue. This is epigenetic drift. It helps explain why older bodies can become more unpredictable. Some cells may overactivate inflammatory programs, while others underperform in repair. The unsettling part is that this drift can happen without any dramatic mutation event. It is more like gradual loss of fidelity, with the regulatory system making more small mistakes as it maintains itself across many cell divisions. That noise can contribute to frailty, slower healing, and increased disease risk, because the body relies on tight coordination. Yet this concept is also strangely empowering. If drift is a loss of signal quality, then interventions that improve cellular maintenance might help preserve clarity. It frames aging as partly a problem of keeping regulatory patterns stable, not only a problem of damage. The body is not just wearing out. It is also losing crisp control, one small wobble at a time. Some long-lived animals show unusually stable epigenetic regulation. Some animals live far longer than their body size and metabolism would suggest, and part of their secret may be unusually stable gene regulation. Species like the naked mole rat and certain whales show remarkable resistance to age-related decline, including lower cancer rates than you might expect for their size or lifespan. Researchers investigate whether their cells maintain cleaner epigenetic patterns over time, preventing the noisy drift that makes aging messy in many species. This is fascinating because it suggests longevity is not only about fixing damage. It may also be about preventing the regulatory system from wandering off course. If a long-lived animal keeps inflammation tightly controlled, keeps repair programs reliably accessible, and prevents cells from slipping into chaotic states, it can delay the cascade that leads to disease. These animals become living proof that long life is biologically possible, not just wishful thinking. They also serve as natural experiments. Evolution has already built multiple solutions to aging, and epigenetics may be one of the core tools it uses. Studying these creatures is like reading nature's hidden instruction manual for staying stable. Hibernation involves sweeping seasonal gene control changes without new DNA. Hibernation is one of the most dramatic examples of biology changing its operating mode without changing its genome. A hibernating animal can drop its heart rate, lower its body temperature, and survive long periods with minimal food, all while protecting vital organs. That requires massive shifts in which genes are active, because the body has to prioritize energy conservation, cellular protection, and safe rewarming later. Epigenetic control helps coordinate those seasonal switches, turning down certain programs and turning up others in a timed sequence. What makes this so captivating is the precision. The animal does not simply slow down. It enters a controlled state that keeps tissues from falling apart. There are also puzzles that feel almost science fiction. How do muscles avoid severe wasting when movement is minimal? How does the brain stay protected when energy is so low? Hibernation suggests that mammals can access deep survival programs that humans only hint at. If we understood those switches, it could inspire new ideas for medicine, trauma care, and organ preservation. Nature already runs a reversible low-power mode, and epigenetics helps manage the switch. Queens and workers share bDNA, yet epigenetics makes roles. In a bee colony, queens and workers can start with the same genetic blueprint, yet their lives diverge into completely different bodies and destinies. The queen grows larger, develops a fully functional reproductive system, and can lay thousands of eggs. Workers become specialized for tasks like foraging, nursing, and defending the hive. This is not a DNA difference. It is a gene regulation difference, shaped by the environment of development. The stunning part is what this implies about possibility. A single genome contains multiple potential life paths, and epigenetics helps choose which path is taken. The colony is like a social organism that uses developmental signals to create the right kind of individual for the job. It is not only about anatomy. It is about behavior too. Worker bees perform complex tasks and shift roles as they age, guided by changes in brain and hormone systems. This is epigenetics as a builder of societies, not just bodies. It shows how the same genetic toolkit can produce radically different outcomes when regulation steers development down different tracks. Royal jelly can steer bee development through gene regulation changes. The difference between a queen and a worker can begin with food. Larvae that are fed royal jelly for longer periods can develop into queens, while those that switch to a different diet typically become workers. This is one of the most famous examples of nutrition directing development, and it becomes even more fascinating when you connect it to gene regulation. Royal jelly contains compounds that influence hormonal signaling and may affect epigenetic enzymes, helping shift which genes are emphasized during critical windows. The result is not a small tweak. It is a full-body transformation with lifelong consequences. That is what makes it feel like a fairy tale with a molecular mechanism. A change in diet during early development can decide fertility, body size, lifespan, and social role. This also forces a deeper question. If a bee can carry multiple developmental futures inside one genome, how many possible bodies exist in other species but never get expressed because the signals never arrive? Bees make the principle visible. Development is not only inheritance. It is instruction plus environment, looked together in timing. Ant castes can form from epigenetic differences, not gene differences. Ant colonies are full of specialists, and in many species, those specialists can arise without major genetic differences. Workers, soldiers, and reproductive individuals can have distinct body shapes, jaw sizes, and behaviors, yet share essentially the same DNA. Epigenetic regulation helps explain how the colony produces the right mix. Signals like diet, pheromones, temperature, and social interactions can steer developing ants toward different forms by changing which growth programs run strongly. In some species, larvae can be directed into soldier pathways that produce huge heads and powerful mandibles, built for defense rather than foraging. What makes this so gripping is that the colony is shaping individuals as if it is designing them. It is a living system that uses regulation to allocate resources and create roles, almost like a factory that can build different models from the same blueprint. Ants remind us that genes are not simply instructions for one outcome. They are a toolkit. Epigenetics decides which tools get used, when, and for what purpose. Plants use epigenetics to remember drought and respond faster later. A plant cannot run from danger, so it learns. When drought hits, plants flip emergency programs that conserve water, protect proteins, and slow growth. What is astonishing is that after the stress ends, some plants stay primed, reacting faster to the next dry spell. This is sometimes called stress memory, and it can involve lasting changes in gene control, not changes in DNA sequence. The next time conditions worsen, the plant can switch on protective genes more quickly, as if it already knows what is coming. That memory can show up in how stomata open and close, how roots explore soil, and how the plant balances survival against growth. It is a quiet form of intelligence built into biology. Epigenetics helps explain how a season of hardship can train a plant for the future, turning experience into faster readiness. The plant's past becomes part of its response speed, and that is breathtaking. Some plants pass stress memories to offspring through epigenetic marks. In some plant experiments, the effects of stress do not end with the stressed plant. Offspring can sometimes show altered readiness, as if they inherited a warning. This is not inheritance of new DNA letters. It is inheritance of gene regulation patterns that survived reproduction. That idea sounds impossible until you remember that plants form seeds while still living through their environment. If stress changes the way certain genes are packaged or tagged in reproductive cells, some of that information can be carried into the next generation. The result can be seedlings that respond differently to drought, heat, or pathogens compared with seedlings from unstressed parents. This is not universal, and it is not always stable across many generations, but it is real enough to reshape how we think about inheritance in plants. It suggests that a plant's life can influence its children's starting settings. Epigenetics turns the environment into a family message, passed along quietly through seeds. Cold exposure can prime flowering genes through lasting epigenetic changes. Some plants will not flower until they have experienced winter. This is not stubbornness. It is a survival strategy. Flowering too early can doom a plant's reproduction, so cold becomes a seasonal checkpoint. The remarkable part is that plants can record that cold exposure in gene control. After a sustained chill, key flowering repressors can be silenced so the plant is ready to bloom when warmer days return. This process is called vernalization, and it depends on lasting regulatory changes that persist even after temperatures rise. It is like the plant leaves itself a note that says, "Winter has happened. It is safe to proceed." When spring arrives, the plant does not need to recheck the past. The gene setting has already been adjusted. This turns temperature into a developmental decision, stored in chromatin and read months later. Epigenetics makes seasons part of the plant's internal logic, linking weather to life timing with incredible precision. Skin cells can be reprogrammed into stem-like cells by resetting epigenetics. A skin cell looks ordinary, but it holds a hidden possibility. With the right signals, scientists can push adult skin cells back into a stem-like state that can become many cell types. This works by resetting key gene control patterns, loosening the cell's identity, and reopening developmental options. The shock is that the DNA never needed rewriting. The information was already there, locked behind layers of regulation. When those locks are lifted, the cell can act young again, at least in its potential. These reprogrammed cells are called induced pluripotent stem cells, and they changed biology overnight. They can be grown in a dish, guided into heart cells, neurons, or pancreatic-like cells, and used to model diseases using a person's own genetic background. It is like making a personalized sandbox of human biology. Epigenetics is the gateway that makes this possible, turning a specialized cell into something flexible and powerful. That reprogramming helped launch modern regenerative medicine. Once scientists could create stem-like cells from adult tissue, medicine gained an entirely new playbook. Researchers could take cells from a patient with a genetic condition, reprogram them, and then watch the disease unfold in the lab in the exact cell type that matters, like neurons for certain brain disorders or heart cells. For rhythm problems. That made drug testing more realistic than using generic cell lines. It also opened the door to building replacement tissues. In some labs, scientists grow mini organs called organoids, tiny simplified versions of brain, gut, or retina that can reveal development in motion. Even when therapies are not ready, the insight is immediate. You can test how a specific person's cells react to a treatment before giving it to the person. The wonder is that this whole revolution began with gene control, not gene editing. Epigenetics made it possible to rewind a cell's identity then steer it forward again. Regenerative medicine is not only about fixing organs. It is about understanding, predicting, and rebuilding biology with precision. Epigenetic barriers are one reason organs do not regrow easily. If you cut a lizard's tail, it can regrow. If you injure a human heart, it mostly forms scar. One reason is that many human cells are locked into their identities so tightly that they cannot easily return to a flexible rebuilding state. Those locks are epigenetic barriers. They protect you from chaos, like cells turning into the wrong tissue or dividing recklessly. But the protection has a cost. When serious injury happens, the body often chooses stability over regeneration. Cells focus on sealing the wound and maintaining function rather than rebuilding the original structure. This is why some organs, like the liver, regenerate better than others, and why the brain and heart are so limited. The thrilling implication is that if we learn to safely loosen specific barriers, we might coax regeneration without triggering dangerous growth. That is the dream behind many therapies, from scar reduction to heart repair. Epigenetics is not just a scientific detail here. It is one of the main reasons your body heals the way it does. Wound healing activates temporary gene programs controlled epigenetically. When you get a cut, your skin does not simply close like a zipper. It launches a timed biological story with distinct phases. First comes clotting to stop bleeding. Then immune cells arrive to clean and defend. Then repair cells migrate, multiply, and rebuild. Each phase requires different genes to turn on and off in a precise sequence. Epigenetic control helps coordinate that schedule by opening access to genes needed now and closing them once their job is done. If those programs stayed on, healing would become destructive, with endless inflammation or uncontrolled tissue growth. If they turn on too weakly, wounds linger and infection risk rises. What makes this captivating is that healing is not only chemistry. It is choreography. The body is reading different chapters of the genome at different times, responding to signals from damage, microbes, and surrounding cells. A scar is the visible result, but underneath is a temporary rewrite of gene activity that transforms ordinary skin into a repair crew, then returns it to normal. Scar formation involves long-term gene activity shifts in skin cells. A scar is not just extra collagen. It is a new, long-term identity for a patch of tissue. After injury, certain cells called fibroblasts can shift into a more active state that produces thick structural material quickly, creating strength fast, even if it is not perfect. In many cases, those cells do not fully return to their earlier behavior. They maintain altered gene activity patterns that keep the area stiffer, less elastic, and less able to grow hair or sweat normally. That is why scar tissue can feel different, look different, and behave differently for years. In some people, the system overshoots, leading to raised scars or keloids, where growth signals stay high beyond what is needed. The exciting part is that understanding scar biology is opening new possibilities. If scarring is partly a long-term gene control state, then targeted treatments might help shift the tissue back toward a more normal program. Epigenetics frames scarring as adjustable biology, not just permanent damage. Metabolism produces molecules that directly feed epigenetic chemical tagging. Your metabolism is not only about energy. It also supplies the raw materials used to control gene activity. Cells break down food into molecules that become building blocks for chemical tags on DNA and histones. That means what your body is doing metabolically can influence how easily certain gene control marks are added or removed. When energy is abundant, the cell may favor growth and building. When energy is scarce, it may favor repair and conservation. Those choices are reinforced by the availability of tagging molecules produced by metabolic pathways. The mind-blowing idea is that gene regulation is partly constrained by what the cell has on hand. Epigenetics is not floating above the body like a separate system. It is wired into the same chemistry that determines hunger, blood sugar, and fuel use. This helps explain why long-term metabolic states, like chronic overnutrition or prolonged stress, can shift gene activity patterns in durable ways. Metabolism is not just a consequence of gene expression. It is also a driver of it. Your gut microbes make compounds that can influence gene regulation. Inside your gut lives a community that acts like an extra organ. These microbes break down fibers you cannot digest and produce compounds that enter your bloodstream and affect your physiology. Some of those compounds can influence gene regulation by interacting with pathways that control chromatin and histone modifications. That means your microbiome can send chemical messages that reach far beyond the gut, influencing immune balance, inflammation, and even brain-related signaling through the gut-brain connection. The striking part is how indirect and yet how real it is. A diet rich in diverse plant fibers can favor microbes that produce helpful metabolites, while a diet low in fiber can reduce those signals. This is one reason identical diets can affect people differently, because the microbes doing the processing are different. Epigenetics helps explain how those microbial products can shift the body's long-term settings. You are not only eating for yourself. You are feeding a chemical factory that helps shape the gene regulation environment you live in every day. Short-chain fatty acids from fiber can affect histone-related processes. When you eat fiber, you are not feeding your body directly so much as feeding the microbes that break it down. One of their most important products is short-chain fatty acids, especially butyrate, which can travel from the gut and influence how cells manage gene access. One way it does this is by interacting with enzymes that modify histones, the protein's DNA wraps around. When histone chemistry shifts, DNA can become easier or harder to read, which changes which genes get used. This helps connect diet to immune balance in a very physical way. In the colon, butyrate can help support the health of the gut lining and encourage calmer immune signaling. It is a startling chain reaction. A bowl of oats or beans becomes a chemical signal that can influence how tightly DNA is packaged in certain cells. That is not vague wellness talk. It is a real route from food to microbes to molecules to gene regulation. Alcohol can disrupt methylation by draining key chemical building blocks. Alcohol does more than stress the liver. It can also interfere with the chemistry that supplies methyl tags, the small marks used to regulate genes. Your cells rely on a carefully balanced flow of nutrients and reactions to produce methyl donors, and alcohol can throw that system off. Over time, heavy drinking can reduce availability of key molecules used in one-carbon metabolism, while increasing oxidative stress that forces the body to spend resources on damage control. That matters because methylation patterns help keep gene activity organized. If methyl supply is strained, important regulatory regions can shift in ways that affect metabolism, inflammation, and cell stability. This is one reason alcohol's effects can feel widespread and slow to reverse. The body is not only dealing with intoxication, it is rebuilding a disrupted chemical economy that supports normal gene regulation. The scary part is that you may feel fine while these deeper systems are being nudged off course. The hopeful part is that reducing intake can give the system room to stabilize again. Folate and related nutrients support the body's methyl tagging supply chain. Folate is not famous because it gives you energy in the moment. It is famous because it helps run the supply chain that keeps methyl tagging possible. Inside cells, folate works with vitamin B12 and other helpers to move single carbon units, through reactions that produce key methyl donor molecules. Those donors are what your cells use to place methyl marks that regulate gene activity. When folate status is low, the system can bottleneck. That can shift homocysteine levels and alter how reliably methyl tags are maintained during cell division. The result is not one simple symptom. It is a subtle vulnerability in regulation, especially in tissues that are renewing or developing. This is why folate matters for more than pregnancy. It supports a basic maintenance pathway used in every age, in every organ, every day. The fascinating idea is that micronutrients are not just extras. They are ingredients for controlling which parts of your genome are active. In a very real way, they help your body keep its gene settings stocked and stable. Air pollution exposure is linked to epigenetic shifts in immune genes. Air pollution is not only an irritant you cough out. Tiny particles can trigger immune responses that ripple through the body, and researchers have linked pollution exposure to changes in methylation patterns near genes involved in inflammation and immune signaling. What makes this unsettling is how measurable it can be. In some studies, people living in higher pollution areas show different epigenetic patterns in blood cells compared with those in cleaner air, even when they feel healthy. These shifts may help explain why pollution exposure is associated with higher risks of cardiovascular problems and other inflammatory conditions. The body can treat polluted air as a repeated low-level threat, and repeated threats can train immune regulation in a lasting way. This turns air quality into more than an environmental issue. It becomes a gene regulation issue. It is also a reminder that health is not only personal choice. Sometimes it is the chemistry you breathe every day, shaping how your immune system sets its baseline. Epigenetics helps reveal that hidden cost. Sunlight affects skin gene expression, partly through chromatin changes. Sunlight is a signal and a stressor at the same time. When ultraviolet light hits skin, cells respond by activating protective programs, including DNA repair pathways and pigment production. To do that quickly, skin cells adjust chromatin, shifting how tightly DNA is packed so certain genes become easier to access. This is one reason tanning and redness are not just surface events. They reflect deeper cellular decisions about defense, repair, and inflammation. Sunlight also connects to vitamin D production, which itself influences gene activity through hormone-like signaling. That means sunlight can push gene programs through multiple routes, some protective and some damaging depending on dose and timing. The fascinating tension is that skin has to balance two goals that can conflict. It must allow enough sunlight-driven chemistry to support normal physiology while preventing UV from overwhelming repair systems. Epigenetics sits inside that balancing act, helping decide which instructions are activated first and how long they stay active. Your skin is constantly negotiating with light. Some medications unintentionally change epigenetic patterns as side effects. Not every drug aims at gene regulation, yet some medications influence it anyway. A striking example is valproate, a medicine used for seizures and mood disorders, which can affect enzymes that modify histones. That can change how accessible certain genes are, which may contribute to both therapeutic effects and side effects. Steroid medications offer another route. They act through receptors that enter the nucleus and alter gene activity programs, sometimes reshaping long-term inflammatory settings when used for extended periods. Even common exposures like long-term proton pump inhibitors or certain antibiotics can indirectly affect gene regulation by shifting nutrient absorption or the microbiome, which changes the chemical environment cells live in. The key idea is not fear, it is realism. Drugs do not operate in isolation. They push on signaling pathways, and signaling pathways often end at gene control. This is why people can respond differently to the same medication, and why long-term use can have effects that appear gradual rather than immediate. Epigenetics helps explain those echoes. Pain sensitivity can be influenced by epigenetic regulation in nerve pathways. Pain is not just a signal from an injury. It is a system that can become sensitized. After repeated inflammation, nerve damage, or persistent stress, pain pathways can shift so that normal sensations feel sharper and discomfort lingers longer. Epigenetic regulation is one mechanism that may help lock in this heightened state. Gene programs in sensory neurons and supporting immune-like cells can change, influencing ion channels, inflammatory mediators, and the threshold for firing pain signals. This helps explain why chronic pain can continue even after the original injury has healed. The body has learned a protective setting, and it keeps running it. It is like turning the volume knob up and then forgetting it is up. This perspective can be strangely comforting. It suggests chronic pain is not imaginary, and it is not purely willpower either. It is biology that has been retuned. It also suggests new treatment angles, aimed not only at blocking pain signals, but at shifting the underlying regulation that keeps the system on high alert. Addiction involves long-lasting gene regulation changes in reward circuits. Addiction is not simply liking something too much. Repeated exposure to addictive substances can reshape reward circuits so that cues, cravings, and stress responses become wired into daily life. In research models, drugs like cocaine can trigger lasting changes in histone modifications and gene activity in the brain's reward regions, altering how neurons respond to stimulation later. That helps explain why cravings can reappear after long periods of abstinence, triggered by a smell, a place, or an emotion. The brain has not only stored a memory, it has adjusted its baseline. Some gene programs related to synaptic strength and dopamine signaling can become easier to reactivate, making relapse risk feel sudden and overpowering. This frames addiction as a learning process with a molecular backbone. The substance does not just create pleasure. It trains the brain to prioritize the substance, to expect it, and to reorganize around it. Epigenetics adds a mechanism for why this can persist, and why recovery often requires time, support, and repeated retraining of the system. Nicotine can remodel chromatin in brain cells exposed repeatedly. Nicotine delivers a fast, reliable signal to the brain's attention and reward systems. With repeated exposure, neurons adapt, and part of that adaptation can involve changes in chromatin that influence gene activity linked to receptor levels, stress signaling, and synaptic plasticity. This helps explain why tolerance and dependence can build even when a person feels they are just having a little. The brain is adjusting its settings to match the repeated chemical pattern. In adolescence, this can be especially concerning because developing brains are already in a highly plastic state, with gene programs actively shaping circuits for motivation and self-control. Nicotine can slip into that process and bias it. The result is a brain that becomes more reactive to nicotine cues and more uncomfortable without nicotine. This is not only habit, it is reconfiguration. Epigenetic remodeling offers one reason quitting can feel like more than stopping a behavior. You are asking the brain to unwind settings it has begun treating as normal, and that unwinding can take time. Epigenetics helps explain why quitting can still leave long shadows. Many people expect quitting to flip a switch. Yet after stopping smoking or other exposures, the body can carry traces of past regulation for a long time. Some gene control patterns change quickly, while others unwind slowly, and some may persist as a kind of biological scar. This can show up as lingering risk, altered inflammatory tone, or persistent sensitivity to cues and stress. The fascinating part is that the shadow is not the same for everyone. Different tissues reset at different speeds, and individual biology, age, and exposure history all matter. Epigenetics helps make sense of that uneven recovery. It also reframes what progress looks like. If regulation changes gradually, an improvement can be real, even when it is not immediately obvious. Over time, healthier signals can push in the opposite direction, helping gene activity programs return toward a steadier baseline. This is why quitting is still one of the most powerful decisions a person can make, even if the benefits unfold on a longer timeline. The body remembers, but it can also relearn. Some epigenetic states can persist through many cell divisions. When a cell divides, it faces a strange challenge. It must copy its DNA and also copy its identity. Otherwise, your body would slowly forget what each tissue is supposed to be. Epigenetic persistence is how that identity survives. A skin stem cell in your scalp divides again and again, yet it keeps producing skin cells, not random tissue, because gene access patterns are passed forward like instructions taped to the blueprint. This stability is powerful and a little scary. It is part of how you stay organized for decades, but it is also how a bad setting can spread. If a growth control program is shut down in a cell that begins to expand, that silenced state can be inherited by its descendants, helping a problem clone itself. The awe is that your body runs on long-lasting molecular memory. Not just memories of events, but memories of roles, copied quietly through time in millions of cell lineages. Yet many epigenetic marks are actively erased and rewritten daily. Some gene settings are meant to last, but others are meant to move. Your body lives in changing conditions, so it constantly edits short-term instructions. Hormones rise and fall. Meals arrive, then stop. Activity ramps up, then quiets. Cells respond by wiping certain regulatory marks and replacing them with new ones, like rewriting today's schedule on a whiteboard. This is why the same body can be alert in the morning, hungry at midday, and sleepy at night, without needing new genes. It is also why recovery is possible. After a stressful day, your biology can step down, rewriting programs tied to vigilance and shifting toward repair. The fascinating part is that this is active work. Cells spend energy maintaining the right settings for the moment, preventing yesterday's emergency program from becoming tomorrow's default. Epigenetics is not only a lock, it is also a reset button that gets pressed again and again, keeping you adaptable. Non-coding RNA can guide gene silencing like a targeted message. Not all useful genetic material becomes a protein. Some RNA molecules act more like instructions that tell the cell where to place silence. They can guide silencing machinery to a specific stretch of DNA, almost like a postal address, so the cell quiets exactly the right region instead of shutting down everything nearby. This is especially important for controlling genomic troublemakers, like repetitive sequences that can misbehave if they become active. In many organisms, RNA-based targeting helps keep these regions suppressed, protecting stability across a lifetime. What makes this mind-blowing is the precision. The cell can use a sequence-based message to find a matching DNA region and then change how that region is packaged and read. It is gene control with guidance. It also expands what information means in biology. Your genome includes not just the parts that build proteins, but also the parts that act like navigation and security systems, directing where silence should land. Tiny microRNAs can dampen protein production without touching DNA letters. MicroRNAs are small, but they behave like powerful dimmer switches. Instead of changing DNA or shutting a gene completely, they can reduce how much protein gets made from a message that already exists. They do this by binding to messenger RNA and interfering with its translation, which is like lowering the volume after the script has already been copied. This matters because biology often needs fine control, not an on or off switch. During development, microRNAs help cells transition cleanly from one stage to another by gently suppressing old programs while new ones ramp up. In disease, the same tool can be misused. If a microRNA that normally keeps growth signals quiet becomes too active or too weak, the balance can tip. The ore is the elegance. With a tiny molecule, the cell can tune thousands of outcomes, shaping protein levels with speed and subtlety. It is regulation that feels more like mixing audio than flipping breakers. Long non-coding RNAs can recruit gene-shutting machinery to exact spots. Some non-coding RNAs are long enough to act like scaffolding. They can bring together multiple proteins, guide them to a DNA region, and help build a silencing complex right where it is needed. This is like assembling a team, handing them a map, and watching them lock a specific door in a huge building. The result can be stable, localized gene quieting that changes how a cell behaves for a long time. What makes this captivating is that it shows regulation can be physical architecture. The RNA is not a passive copy. It is part of the structure of control, organizing molecules in space. This helps explain how cells can manage very selective silencing without accidentally shutting down neighboring genes that are essential. It also hints at a future where medicine might target these RNAs to shift gene programs more precisely, like changing which rooms are accessible without renovating the entire house. Epigenetics is not only chemistry, it is also choreography and construction. Chromatin folding determines which genes can even be reached. Your DNA is not laid out like a straight string. It is folded into loops and neighborhoods inside the nucleus. That folding creates a practical truth. Some genes are physically reachable by the cell's reading machinery, and others are tucked away behind layers of packing. So genre regulation is not only about which switches exist, it is also about whether the switch is even accessible today. Cells use this to stay sane. By folding DNA into active zones and quiet zones, they reduce chaos and keep cell identity stable. The thrill is that folding patterns differ across cell types. A region that is open and busy in an immune cell might be buried in a neuron, simply because the internal architecture is different. This also helps explain why disruptions can be serious. If folding boundaries weaken, genes can be exposed to the wrong signals, like a private room suddenly opening onto a noisy street. The genome is not just written, it is arranged. DNA can loop so far away switches control genes like remote controls. Some of the most important gene switches are not parked next to the genes they control. They can sit far away along the DNA strand, then loop through space to touch the gene's control region when it is time to act. This sounds like science fiction, but it is one reason small changes in distant DNA regions can have big effects. A developmental switch that guides limb growth, for example, can be located far from the gene it influences, yet still act as the master dial for when and where that gene turns on. The beauty is that looping allows reuse. The same gene can be controlled differently in different body parts by connecting to different distant switches, like choosing different remotes for the same device. It is also a reminder that genetic cause and effect is not always local. The important instruction might be nowhere near the gene itself. Epigenetics and DNA architecture together turn the genome into a three-dimensional control system. One enhancer region can influence multiple genes in a neighborhood. Sometimes, one powerful switch does not control only one gene. It can coordinate several nearby genes, turning them into a team that rises and falls together. This is especially useful when multiple genes are needed for one job, like building a structure, running a biochemical pathway, or guiding a developmental step. Instead of managing each gene separately, the cell can use a shared enhancer region that acts like a neighborhood announcement, boosting activity across a local cluster. The fascinating part is how this creates synchronized behavior. Genes can be co-activated at the right time, in the right cell type, without needing independent triggers for each one. It also means disruption can ripple. If that enhancer is blocked, several genes may drop at once, like a street losing power because one transformer failed. This helps explain why some DNA variants, far from genes, can still matter. They may be changing a shared control hub, not a single, isolated instruction. Regulation often works in groups. A single gene can have multiple on switches for different tissues. One gene can be used in several parts of the body, but for different reasons. To make that work safely, the gene often has multiple switches, each designed to turn it on in a specific tissue or at a specific life stage. One switch might activate the gene in the heart, another in the brain, another during early development only. This is why a change in one switch can cause a very specific effect without breaking the gene everywhere. It is also why genetics can feel confusing. A person can have a perfectly normal gene sequence, yet still have a problem in one organ because the local switch is faulty. The "or" here is modular design. The genome builds control panels, not just parts. It can reuse the same gene like a tool, but only where the right switch grants permission. This also gives evolution flexibility. It can tweak when and where a gene is used without rewriting the entire tool itself. Epigenetics explains how context decides which switch is used. Your cells do not treat all switches equally. They choose based on context. Signals like hormones, inflammation, nutrition, and developmental stage can make one enhancer easy to access and another harder to reach. That is how the same gene can behave differently in different moments. In childhood, one switch might dominate to support growth. In adulthood, a different switch may take over to support maintenance. Under stress, yet another switch can become more available, changing the gene's output to match the situation. This is why biology can be both stable and responsive. The underlying DNA stays the same, but the priority list of switches shifts with circumstances. It is also why the same exposure can have different effects in different people. If their baseline context differs, the switch that gets used can differ too. Epigenetics turns genes into a responsive system rather than a fixed script. It is the reason what happens depends so much on when and where. Some autoimmune diseases involve epigenetic misfiring in immune cell identity. Your immune system depends on identity. A T cell must behave like a T cell, a peacekeeper when appropriate and a fighter when necessary. In autoimmune disease, that identity can blur. Instead of recognizing the body as home, immune cells can start treating it like a threat. Epigenetic misfiring is one way this can happen. Regulatory settings that normally keep inflammatory genes quiet can loosen, while genes that enforce tolerance can become harder to activate. The result is not one dramatic malfunction. It is a gradual drift toward overreaction. This helps explain why autoimmune conditions can flare and fade, and why triggers like infection or prolonged stress can tip the balance. The immune system is not only detecting enemies, it is constantly reading context, deciding when to escalate and when to stand down. If the settings that govern that decision become unstable, the body's defenses can turn inward. Epigenetics gives a concrete mechanism for why the immune system can lose its sense of self. Asthma has been linked to epigenetic patterns shaped by environment. Asthma is often described as sensitive airways, but the deeper story is a nervous and immune system that can become too reactive to ordinary exposures. The environment can shape that reactivity. Studies have linked factors like air pollution, secondhand smoke, early life infections, and even indoor allergens to epigenetic differences in genes involved in immune signaling and airway inflammation. What makes this fascinating is that it can help explain why ASMR risk varies so much between neighborhoods, families, and childhood histories, even when genetics are similar. The body is not only inheriting risk, it is receiving training signals about what the world feels like. If the immune system is repeatedly nudged toward an allergic-style response, it can become quicker to clamp down the airways in defense. That defense can become excessive, producing wheeze and tightness. Epigenetics reframes asthma as partly a learned setting in biology, shaped by exposure patterns that leave long-term marks on how the airways respond. Obesity risk involves gene regulation changes, not just willpower. Weight is not governed by motivation alone. Your body has systems that decide hunger intensity, satiety timing, energy use, and how strongly food cues pull your attention. Those systems can shift through gene regulation. Long-term sleep loss, chronic stress, repeated dieting, and highly processed food environments can all influence hormonal signals like leptin and insulin, which feed back into gene activity in brain, fat tissue. Over time, the body can become better at storing energy and worse at sensing fullness, not because a person lacks character, but because biology has adapted to repeated signals. This helps explain why weight regain is common after rapid loss, and why two people can eat similarly yet experience different outcomes. Epigenetics offers a mechanism for how the body can reset its baseline. It also reshapes the conversation. If regulation is involved, then sustainable strategies matter more than extreme bursts. The body responds to patterns. When patterns change, gene programs can gradually shift, and the effort becomes less like fighting yourself. Type 2 diabetes includes epigenetic shifts in insulin-related pathways. Type 2 diabetes is often framed as sugar trouble, but it is really a breakdown in communication between tissues that handle energy. Muscle, liver, and fat cells must respond properly to insulin, and the pancreas must adjust insulin output without burning out. Epigenetic shifts can be part of why that communication deteriorates. Chronic overnutrition, inflammation, and sedentary patterns can nudge gene activity toward insulin resistance, altering how cells transport glucose and manage fat storage. Over time, the pancreas may be pushed to overproduce insulin, then struggle to keep up. What makes this compelling is that early changes can be silent. Blood sugar can look fine while gene programs are already drifting toward resistance. Epigenetics also helps explain metabolic memory, where early periods of poor control can leave lasting effects even after improvement, because some regulatory changes unwind slowly. The hopeful side is that lifestyle and medication can improve function, and gene regulation can shift with sustained signals. Diabetes is not just one number. It is a long story of cellular settings changing over time. Heart disease risk can reflect long-term gene control changes in vessels. Blood vessels are not passive pipes. Their inner lining senses pressure, chemicals, and immune signals, then adjusts tone and repair. Over years, repeated strain can change how vessel cells behave. High blood pressure, smoking, chronic stress, and systemic inflammation can push endothelial cells toward a more reactive state, with gene programs that favor clotting, stiffness, and inflammatory signaling. Those are gene control shifts, not necessarily gene breaks. This helps explain why heart disease is often a slow build. The vessel wall gradually becomes less flexible, more irritated, and more likely to form plaque. Epigenetics adds a mechanism for why early exposures matter. A period of uncontrolled pressure or persistent inflammation can leave regulatory patterns that keep vessels on edge. It also clarifies why prevention works. Lowering blood pressure, improving sleep, and reducing inflammation are not just lifestyle slogans. They change the signals that vessels live in every day, which can gradually steer joint activity back towards smoother function. Risk is not only inherited, it can be written into vessel behavior over time. Depression has been associated with altered epigenetic regulation in stress circuitry. Depression is not simply sadness. It can involve changes in how the brain processes reward, threat, and recovery. Stress circuitry is central here. Studies have linked depression and chronic stress exposure to epigenetic differences in genes involved in stress hormone signaling and brain plasticity, encoding pathways that influence how neurons adapt and connect. The striking idea is that prolonged stress can shift the brain's settings, making negative information feel heavier and pleasure feel muted. That shift can become self-sustaining. Poor sleep worsens stress sensitivity. Stress sensitivity worsens sleep, and the brain's regulatory patterns keep reinforcing the loop. Epigenetics does not reduce depression to a single cause. It adds a mechanism for why experience can leave durable effects on mood and motivation. It also supports a compassionate view. If regulation has shifted, then snap out of it is a cruel misunderstanding. Recovery often requires repeated signals of safety and support, delivered through therapy, routine, connection, and sometimes medication. The brain can change, but it changes through biology, not scolding. Antidepressants may work partly by nudging gene activity programs over time. One reason antidepressants can take weeks to show full effects is that they may be doing more than changing chemical levels in the moment. Over time, altered neurotransmitter signaling can shift gene activity programs involved in neural plasticity, stress response, and synaptic remodeling. That means treatment can gradually help the brain become more flexible again, not just less distressed. Some research points to changes in pathways related to growth factors and connectivity, which fits the lived experience of many people. Mood improves as the brain becomes less stuck. This framing also helps explain why therapy and medication can be powerful together. Medication can lower the biological noise and widen the window for learning new patterns, while therapy provides new experiences and coping strategies that the brain can encode. Epigenetics offers a bridge between fast chemistry and slow change. It suggests that improvement is not always immediate, because the brain is not only turning down symptoms. It is adjusting deeper programs that govern how it responds to life. That makes gradual progress feel logical, not mysterious. Brain development relies on precisely timed epigenetic opening and closing. Building a brain is like staging thousands of carefully timed launches. Neurons must form, migrate, connect, then prune extra connections so circuits become efficient. Each step requires different gene programs to run in the right order. Epigenetic opening and closing is how the sequence stays coordinated. During early development, certain regions of the genome become accessible so cells can commit to being neurons. Later, different regions open to guide wiring and synapse formation. After that, other programs ramp up to support myelination and long-term stability. If timing slips, the results can be profound. A program that stays open too long can disrupt pruning. A program that opens too late can impair connectivity. This is why many neurodevelopmental conditions are linked not only to mutations, but also to disruptions in regulation and timing. The awe here is how little room for error exists, and yet how reliably development succeeds. Epigenetics acts like a scheduling system, ensuring the right instructions are readable at the right moments, then tucked away when their job is done. Language-related brain circuits form alongside waves of gene regulation. Language feels effortless once you have it, but building language circuitry is one of the most complex developmental achievements in humans. Babies must tune their hearing to the sounds of their environment, map those sounds to meaning, and coordinate perception with motor control for speech. That requires waves of gene regulation that shape auditory processing, timing circuits, and the fine control of mouth and tongue movements. Epigenetic mechanisms help manage these waves by controlling when certain developmental genes are active and when they quiet down. This may help explain why early exposure to rich language environments matters so much. The brain is in a sensitive window where it is building and refining circuits at high speed. It also helps explain why learning new languages is usually easier early in life. Some developmental programs become less accessible later, not because the brain stops being capable, but because the priorities and plasticity settings change. Language is not only learned through ears and practice. It is built through timed biology that makes learning efficient when the window is open. Puberty involves coordinated epigenetic changes that unlock new hormonal programs. Puberty is a biological switchboard coming online. The brain begins sending signals that activate the reproductive hormone axis, and the body responds with growth spurts, changes in body composition, and the maturation of sexual characteristics. This does not happen by accident. It requires coordinated changes in gene activity across the brain, pituitary, gonads, and many tissues. Epigenetic regulation helps unlock the timing. Genes that kept the system quiet during childhood become less restrained, while genes that drive hormone production and sensitivity become more accessible. What makes this fascinating is that puberty timing is influenced by many signals, including nutrition, stress, and overall health. The body appears to integrate these cues before committing to the transition. That integration likely feeds into regulatory systems that decide readiness. Puberty also reshapes the brain. Emotional and reward circuits change, which helps explain why adolescence can feel intense and unpredictable. Epigenetics frames puberty as a planned reprogramming event, where the body opens new chapters of the genome and commits to a new stage of life. Menopause timing may relate to epigenetic aging in reproductive tissues. Menopause is not just a birthday milestone. It reflects a long biological countdown inside the ovaries, where follicles are gradually depleted and the reproductive system shifts into a new mode. Researchers study whether epigenetic aging patterns in reproductive tissues track this timing, because gene regulation helps govern how cells maintain quality control, respond to hormones, and manage CAS. Inflammation. If the regulatory age of these tissues advances faster, the system may reach its transition earlier. If it stays more stable, the transition may come later. What makes this captivating is that menopause timing varies widely between individuals, and that variation is linked to health outcomes across bone, heart, and metabolic systems. Epigenetics offers a mechanism that is neither pure genetics nor pure lifestyle. It is biology keeping a record of time and conditions. It also suggests a future where doctors could estimate reproductive aging more precisely than guesswork, giving people better planning and earlier support when the system seems to be aging faster than expected. Sperm and eggs carry epigenetic information as well as DNA. When people think about inheritance, they picture DNA letters being passed down like a typed recipe. But sperm and eggs also carry a layer of gene control information that helps guide early development. This includes patterns of methylation in key regions and packages of RNA and proteins that shape how the embryo starts using its genome. The wonder is that the embryo's first steps depend on more than the DNA sequence. It depends on how that sequence arrives. This helps explain why the same genetic sequence can behave differently depending on context at conception. It also explains why gametes are so carefully produced and protected. Their job is not only to deliver genes, but to deliver a starter kit for gene usage. That starter kit can influence early cell divisions, the first identity decisions, and the stability of the developing embryo. Epigenetics makes inheritance feel less like passing a book and more like passing a book with bookmarks, highlights, and notes that help the next reader begin. Most epigenetic marks reset between generations, but not all always. A new generation cannot simply inherit every gene setting from the previous one, because sperm and egg lived very different lives. So early development includes a sweeping reset that clears many regulatory marks, allowing the embryo to become any cell type. That reset is one of biology's most dramatic cleanups. Yet it is not perfectly total. Certain regions resist erasure, especially those tied to parent-specific expression rules and genomic stability. This creates a fascinating tension. The body aims to start fresh, but it also preserves a small set of essential instructions about how to run the genome safely. Scientists study which marks escape resetting and why, because those exceptions are where inherited epigenetic effects could, in theory, slip through. The key is precision. It is not that everything is passed down. It is that a few carefully protected categories can be. That makes epigenetic inheritance both plausible and limited. It is not a magical pipeline of acquired traits. It is a narrow doorway that biology mostly keeps closed, with a few guarded keys. Some animal studies show stress effects that echo into descendants. In animal research, scientists can control environments tightly enough to ask a startling question. Can stress in one generation influence biology in the next? Some studies suggest echoes that persist beyond the directly exposed individuals, such as changes in stress reactivity, metabolism, or behavior in descendants. The proposed mechanisms often involve altered regulation in reproductive cells, including shifts in small RNAs or methylation patterns that affect early development. What makes this so gripping is the idea of a body sending a warning forward, not as a conscious message, but as altered settings that tune how offspring respond to danger and scarcity. These effects are not always consistent across labs or species, and they can fade over generations, which is important. Still, the possibility forces a new view of heredity. It suggests that life experience might sometimes influence descendants through biology that does not require new DNA mutations. Even if these effects are limited, they are scientifically profound. They hint that inheritance can include traces of environment, at least under certain conditions, in certain species. Human evidence for inherited epigenetic effects is suggestive, not settled. In humans, the same question becomes much harder. You cannot assign people to controlled stress, famine, or toxins for science, and family environments are tangled with genetics, culture, and socioeconomic factors. That makes it difficult to prove that a biological echo is truly inherited through epigenetic mechanisms rather than shared conditions. Some historical studies and cohort data report associations between ancestral exposures and later outcomes in descendants, and some epigenetic differences have been measured in those descendants. That is intriguing, but it is not a final verdict. Effects can be small, tissue-specific, and influenced by many confounders. Another challenge is that most epigenetic marks reset during early development, which limits what could be transmitted. The most honest position is excitement with caution. There are hints worth studying, but strong claims outrun the evidence. This matters because the topic is emotionally charged. Epigenetics can deepen empathy without turning into destiny stories. The science is pointing toward possibilities, not guarantees. and the difference matters. Epigenetics is a major reason one mutation can have many outcomes. A mutation is often described like a broken part, but its impact depends on where and when the gene is actually used. Two people can carry the same variant and show very different outcomes because their gene regulation context is different. In one person, the gene may be highly active in a vulnerable tissue at a critical time, so the variant matters more. In another person, the gene may be less active, compensated by related pathways, or buffered by a different developmental program. Epigenetics helps explain these differences by shaping access, timing, and intensity of gene expression. This is why having the mutation is not always the whole story. Penetrance and severity depend on the regulatory environment the mutation lives inside. The fascination here is that biology is not a simple chain from DNA to fate. It is an interaction between code and control. Epigenetics can amplify a mutation, soften it, redirect it, or keep it mostly quiet until the wrong context arrives. The same genetic change can play different roles in different bodies. It also explains why the same drug can affect people differently. Two patients can take the same medication at the same dose and have completely different experiences. One improves quickly, another feels nothing. Another has side effects that seem unfair. Part of this is genetics, like differences in drug metabolism enzymes. But epigenetics adds another layer. Drug targets are proteins made from genes, and epigenetic settings influence how much of those targets are present in specific tissues. If a receptor gene is more active in one person's relevant tissue, the drug may have a stronger effect. If it is quieter, the drug may barely find its target. Epigenetic patterns can also shape liver enzymes and transporters that move drugs around the body, affecting exposure and clearance. This turns drug response into a context problem, not just a chemistry problem. It also explains why timing and health state matter. Inflammation, stress, and sleep can shift gene programs that change sensitivity. Epigenetics supports the idea that medicine should become more personal, because bodies are not identical environments for the same pill. Precision medicine increasingly measures epigenetic markers to guide treatment choices. Precision medicine is moving beyond looking only at DNA sequence. In cancer care especially, clinicians often assess gene activity states and epigenetic markers to understand what a tumor is doing, not just what mutations it carries. Methylation patterns can help classify certain brain tumors more accurately than appearance alone, and epigenetic features can point toward which therapies are more likely to work. Researchers also study epigenetic signals in blood as potential early indicators of disease risk or treatment response, aiming for tests that reveal what tissues are experiencing in real time. The excitement is practical. Epigenetics captures the current state of a system, shaped by both genetics and environment. That can make it more actionable than a static genome in some situations. It can also help monitor progress. If a treatment is shifting a harmful program back toward normal, epigenetic markers may reflect that change before symptoms do. This is the promise of measuring biology as it is behaving now. Precision becomes less about guessing and more about reading the body's settings and responding intelligently. Future therapies may edit gene control without editing the gene itself. Gene editing changes the DNA letters. Epigenetic editing aims at something different, changing how a gene is used without altering the sequence. Scientists are developing tools that can be guided to a specific gene region and then add or remove regulatory marks, effectively turning activity up or down with precision. The appeal is huge. If a disease involves a helpful gene being too quiet, you could try to increase its activity without rewriting the gene. If a harmful program is too loud, you could try to dampen it without cutting DNA. This approach could be safer in some contexts, because it may be reversible and does not permanently alter the code. It also fits many real diseases, which involve misregulated pathways rather than broken sequences. The challenge is targeting. You must change the right tissue, the right cells, and the right degree, without off-target shifts that create new problems. Still, the concept is breathtaking. It treats disease as a settings problem, and therapy as a calibrated adjustment, closer to restoring balance than redesigning the genome. Epigenetics turns your genome from a script into a responsive living system. A script implies one fixed story. Epigenetics reveals something more realistic, a genome that behaves like an instrument you can play within limits in response to conditions. The same DNA can support growth, healing, learning, adaptation, and survival, because cells are constantly choosing what to read, when to read it, and how intensely to run it. That choice is shaped by development, hormones, immune signals, sleep, and environment. It is also shaped by randomness and history, which is why outcomes can be unpredictable even with the same genes. This view is powerful because it dissolves false simplicity. You are not a puppet of DNA, and you are not a blank slate either. You are a system built to respond. Epigenetics also gives a language for hope without hype. Many settings can shift with sustained signals and good conditions, but not everything is easily changeable, and not every mark is reversible. The awe is in the truth. Your biology is dynamic, listening, and adaptable, and your genome is not a destiny sentence. It is a responsive operating system. As we come to the end of this journey, let everything you've heard begin to settle gently, like snow drifting onto a quiet landscape. Tonight, you've wandered through a hidden layer of life, one where tiny signals shape growth, memory, healing, and change. You've glimpsed how experience can leave soft impressions on biology, how cells listen, adapt, and remember, and how the body is never frozen in a single state. It is always responding, always adjusting, always learning. These ideas do not need to be held tightly. They are meant to drift. Imagine them like constellations overhead, vast and intricate, yet calm. Your genes are there, steady and patient, while the quiet rhythms of life move around them, guiding when things wake and when they rest. Nothing here demands effort. There is nothing to solve and nothing to remember perfectly. The wonder can simply fade into the background, becoming a gentle hum beneath your thoughts. If you've enjoyed this slow exploration, you're always welcome to support the channel by liking, subscribing, or leaving a quiet comment below. And if you happen to still be awake, another gentle video will appear on your screen, ready to carry you even deeper into rest. But for now, let your breathing slow. Let your shoulders soften. Allow the weight of the day to loosen its grip. You've given your mind something peaceful to wander through, and now it can let go. Sleep well, and good night.